so two things. First, it is often said that relativity and quantum mechanics cannot be reconciled. That's true for the relativistic theory of gravity. People have not yet come up with a completely satisfactory theory of quantum gravity. But that's not at all true for special relativity, which is just the theory of motion without substantial accelerations. Special relativity has long been reconciled with quantum mechanics, and it's not just used for esoteric things like particle physics. It's used for things like understanding magnetic effects and inner shell electrons in condensed matter physics. And so here is a good book on it that I used to sometimes go and read in the library in grad school. And also, for rarely purchased books, you see one of the quirks of Amazon's classification system, that somehow this has gotten classified as a religious studies book. It reminds me of the time when I found a quantum optics book listed on Amazon that had somehow been classified as a children's book. So I wrote a fake book review about how much I enjoyed reading it to my little nephew before bedtime. And then eventually somebody at Amazon got the hint and took it down. The other thing that...
Professor, we can't see your screen.
Oh, sorry about that. Okay, now, so let me go back to that. Yeah, this book by Paul Strange, which somehow Amazon has classified as a religious studies book for reasons completely beyond me. Also, I am going to indulge myself and use recent news as a tipping off point to mention a cool thing in biomedical optics. There's this thing called photodynamic therapy, which strangely enough is tangentially relevant, although not in the way intended, to something that a reality TV star recently said. Photodynamic therapy, the idea is this. There's a whole lot of drugs out there that are really good at killing tumors. The problem is that they're also really good at killing the rest of the body. If all you need to do to kill a tumor was administer something that will kill a slightly malfunctioning human cell, then curing cancer would be easy. The problem is that anything that kills a slightly malfunctioning human cell is very, very, very likely to kill other human cells. So chemotherapy is hard. So what people sometimes do is that they use, they take the cancer drug and they chemically modify it so that the molecule won't actually do anything until you shine light on it. And then once you shine light on it, it becomes very, very deadly. And so they'll administer this, it goes in the bloodstream and infiltrates the whole body. A lot of it infiltrates the tumors because tumors actually have more blood vessels than similar tissue or the tissue that they originated from. So now you got all sorts of, you got a whole bunch of this drug inside the tumor, but it's in an inactive form that won't do anything. Well, what good is that? Well, here's what good it is. A lot of tumors are accessible in some ways. You can stick a tube into the body, down the esophagus, down the windpipe, through the colon, through the urethra, through wherever. And yes, I know this all sounds really, really gross. Medicine is often that way, but you can stick some sort of fiber optic probe into whatever part of the body you need to and get that fiber optic probe in the vicinity of the tumor, which is full of a drug that isn't working. You turn on the light and suddenly that drug is working. And there's actually been a lot of research on that over the years. And people have even used that sometimes for infectious diseases, because imagine you administer an antibiotic. Well, on the one hand, that antibiotic does a very good thing. It kills the bacteria infecting you. It also does a bad thing. All antibiotics, as we have learned from Darwinian evolution over the past several decades, will cause some bacteria to evolve resistance. Some bacteria are not quite completely killed. Some of them just barely manage to survive it. The ones that do barely manage to survive the antibiotic pass on whatever genes enabled them to do that, and the next thing you know, you've got drug-resistant bacteria. So what if we had an antibiotic that doesn't do anything unless you shine light on it? Well, that wouldn't be good if the infection is in the bloodstream. But if the infection is localized to one specific part of the body, then again, what you could do is you could shine light on that. And so I have seen some work on that. So at this point, some of you may be tempted to think that reality TV stars actually do know something about medicine, but here's the problem. Photodynamic therapy is rarely done with ultraviolet light for two reasons. For one, ultraviolet light tends to damage the body. You don't really want to say, okay, we're going to attack this tumor by shining something on it that causes cancer. The other problem with using UV is that UV doesn't travel very far through tissue. So it wouldn't infiltrate the tumor or infiltrate the infected tissue. So they usually use infrared light, not UV light. So I would strongly recommend that people not do that. But nonetheless, since it reminded me of a fascinating topic from biomedical optics, I thought it was worth mentioning and also explaining that at some point you might hear people say, actually, doctors do sometimes shine light inside the body to cure diseases. Yes, but they rarely shine UV light inside the body, partly because it can be dangerous and partly because it's actually infrared light that's most effective at getting tissue. A good piece of evidence for this is to shine a flashlight through your hand. I'm sure everybody has at some point shined a flashlight through your hand, and you see that red light gets through. And of course, that's because the blood is red, so it absorbs everything except red. Red light also gets scattered less. So red light gets at least partially through your tissue. Infrared light gets through the tissue even more effectively. Green and blue and UV, not so much. Any questions?
Yeah, since this would be done at a localized part of the body, would it have to be on the surface of whatever the light would be shining on inside that body part? So it couldn't be somewhere deep inside, a few centimeters beneath the surface?
Yeah, so you're probably not going to use it for brain cancer or liver cancer, but colon cancer, those polyps are visible with probes. Certain kinds of lung cancer, I'm not an expert on, but I know that doctors stick probes down the trachea. Certain kinds of esophageal cancer, depending on where it is, quite possibly, because that infrared light could go some distance through the tissue. Other questions? Probably bladder cancer, probably certain gynecological cancers, any cancer that doctors are able to scope. And, you know, I know it's not, I wouldn't normally talk about these sorts of things, but this is actually how it's actually a pretty important topic for biomedical optics, is making scopes and probes that can go into the throat, into the esophagus, into the sinuses, into whatever, making those cameras, making the other types of probes there, making the various types of endoscopes, and actually bringing a whole bunch of very powerful optical tools to bear to put multiple types of optical tools on one endoscope enables some pretty amazing diagnostics. And at the same time, they can do interventions that way. You know, they can actually, when they go in and image, say, colon cancer, they can actually remove the colon cancer. They can attach tools to the end of that probe so that they can not only see the developing cancer, but actually remove it in early stages. Other questions? All right, then let's go from slow-moving mammals to fast-moving relativistic objects. So we're going to be talking about the barn door paradox today. We're going to be talking about what happens when objects change their length and how this relates to the simultaneity of two events. So we have to start by talking about very carefully, what does it mean to measure the length of an object? The length of an object in a given reference frame is the distance between two detectors that simultaneously measure events at one end of the object and the other. So the way you would measure the length of a train, well, if the train is standing still, you just run a tape measure down it. But if the train is moving and you're on the ground, then you basically put 2 detectors on the track, or you probably put a whole bunch of detectors on the track, here, 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 all along there. And then you have them at a prearranged time, look and see if there's a train in front of them. And so the 2 detectors that observe the edges of the train, those would be the distance between those 2 would be the length of the train. Another way you could do it is that you could set things up based on your knowledge of its motion so that the center of the train will be directly ahead of this light source, and pulses of light arrive at detector 1 and detector 2. And the distances between those detectors when they are at the opposite ends of the train give you the length of the train. So length is a very subtle thing in relativity. It's the distance between detectors that observe simultaneous events at opposite ends of the object. And of course, we know that distance shrinks in relativity because we talked a couple times about an example where you've got a fast-moving object. I say that its velocity is delta x over delta t, but the people on that object, on that alien ship, say, believe that its velocity is that my velocity is minus delta x prime over delta t prime. And we know that delta t prime is the proper time measured going from here to here, and it's a constant velocity in this case. So that's delta t square root of 1 minus v squared. So if we put all that together, delta x prime is v delta t square root of 1 minus v squared, delta x square root of 1 minus v squared, and the distance shrinks. Any questions? All right. So now we get to a paradox. We've got a small building, which for some reason they call a barn. They say it's 8 nanoseconds wide. I don't know. Well, let's see here. 1 nanosecond would be 0.3 meters. So 8 nanoseconds would be just a couple meters, almost 3 meters. I don't know of any barn that's 3 meters, but whatever. It's called the barn door paradox. The barn is 8 nanoseconds from side to side. We could have doors here and here that are usually open. And somebody's running, and they're holding a pole, and that pole would be 10 nanoseconds, or about 10 feet long, in the runner's reference frame. If the runner had stopped and was just standing there at rest with respect to you, we would all say that that pole is 10 nanoseconds long. Then the runner starts running, and it shrinks and they're going at a velocity of 0.6. So the length of it shrinks by this factor. We plug in all the numbers, we get that it's 8 nanoseconds long. So now the pole in our reference frame is the same length as the building in our reference frame. And so we could momentarily close this door and that door. Probably the way to visualize this is with like those sliding doors in science fiction shows. Whenever somebody walks through a portal in a spaceship, they walk up to the door and the doors go and then they go. So you could momentarily open and close these doors, and the runner would be inside the barn for that moment, and there'd be no paradox. We wouldn't be chopping off the ends of the pole. This 8 nanosecond pole would fit inside this 8 nanosecond building. Any questions so far? Even before we get to the paradox on the next slide, consider this. The number of atoms in that pole doesn't change. If somebody starts running, it's not like they suddenly have fewer atoms in themselves, nor do they have fewer atoms in the pole that they're holding. So somehow the number of atoms present in that pole has decreased. And yet the pole has gotten smaller, which could only mean that the atoms have gotten closer to each other. And so one question we could ask is, how is it that these atoms get closer to each other? Is someone exerting a force on them? If they're getting closer to each other, wouldn't the atoms be repelling each other very strongly? You know, normally they're at an equilibrium separation from each other. Then they get closer. They're no longer at an equilibrium separation. And the answer to that is something that we're not going to fully explore this semester, but we will get to it in the last week. Atoms repel each other because the positively charged nuclei get too close to each other, and the negatively charged electrons either have to press together to get between those two nuclei, in which case they're repelling each other because they're at a distance that they don't really want to be at, or the electrons are all spread out, the protons are close together. The details of those interatomic forces are complicated, but they all come from electrical repulsions and attractions. And electrical forces change when you jump to different reference frames. So according to us in our reference frame, yes, we see the atoms inside the pole all get closer to each other. We also see the forces between those atoms change. The runner doesn't see atoms get closer to each other, and the runner doesn't see the forces between those atoms change. The runner does see the atoms in the barn get closer to each other, and the runner does see the forces between those atoms change. So I can't give you a completely satisfactory calculation. Frankly, if you want to know more about seeing these calculations of interatomic forces in different reference frames, you should read Paul Strange's book, which I just recommended a little while ago. But what I can say is that it works out. It works out because it's not just space and time that change, it's also electricity and magnetism that change. And in fact, Einstein's first paper on relativity was not titled on the relativity of space and time. It wasn't titled something about on signals to different observers. It wasn't titled something about the universe all being relative, man. It was titled On the Electrodynamics of Moving Bodies, and he was concerned with precisely this problem. In order to make things work out so that the speed of light was constant to all observers, he realized that space would have to shrink when you go from one reference frame to another, and so that's what his paper was on. Any questions? Okay. So the problem to the runner is that the building moves left with velocity 0.6. So the building gets contracted from 8 nanoseconds wide to 8 times the square root of 1 minus 0.6 squared, or 8 nanoseconds times 0.8, or 0.64 nanoseconds. So if both of these doors close when this tip of the pole gets here, then we've got a problem. If they are both closed at the same time, they're going to chop off the end of the pole. Any ideas on how we might reconcile this? Well, it's written on the page here. I said that the closing of these two doors was simultaneous in the rest frame of the building, but it's not simultaneous in the frame of the person who's holding the pole. I can't say that they're running in their frame. In their frame, they're definitely moving their legs, and the motion of their legs is burning calories, but they think that they're moving their legs to stand still on a treadmill. All right. Events that are spatially separated may be simultaneous in one frame, but not be simultaneous in another reference frame. So let's see, we've got the home frame, the building's at rest. We've got event A, the left door closes. Event B, the right door closes. Event A happens at XA equals 0, TA equals 0. Events B and C. B is the runner standing in the middle of the building. C is the right door closing. So event B happens at t equals 0 and x equals 4 nanoseconds. And event C, the right door closing, happens at xc equals 8 nanoseconds and tc equals 0. But x prime and t prime are different. All right? X prime is x minus beta t over square root of 1 minus beta squared. And t prime is t minus beta x over square root of 1 minus beta squared. And remember that square root of 1 minus beta squared is 0.8. So x prime a is 0 minus 0.6 times 0, which is 0. T prime a is 0 minus 0.6 times 0, which is 0. And that's fine. That just means that we've synchronized everything so that these two frames match up here. All right, these two frames match up for an event happening at x equals 0 and t equals 0. We've set up our coordinate system. We've synchronized our stopwatches so that our stopwatches read 0 when this object is here. All right, now let's talk about x prime b. Well, x prime b is 4 nanoseconds minus 0.6 times 0 over 0.8, or 4 nanoseconds over 0.8, or 5 nanoseconds. In t prime b, plug in all of this, it's minus 3 nanoseconds. Why is it that the event that we call someone standing in the middle of the barn is happening at x equals 5 nanoseconds? And I'm not going to move to the next slide until someone answers this. Why does it make sense that in the runner's frame, the person who's at the middle of the pole is at a position of 5 nanoseconds when somebody on the ground says that they're in the middle of the barn? And I am not going to move on until someone hazards a guess at this. You can say it out loud, you can type it into the chat window, but someone's got to hazard a guess at this. I'll sit here and text my friends until someone hazards a guess at this.
Well, since either end of the barn, events A and event C from the observer who is running occur at different times to that observer, then we can say that the distance, the lengths to those events are also different. It's going to be equal just as the time isn't the same.
Yeah, that's part of it, but there's something much more basic about why we would expect that person holding the center of the pole to be at x equals 5 nanoseconds. Think about the length of the pole. In that person's reference frame, is the pole moving?
No.
Correct. The pole's not moving. In the pole's reference frame, it's 10 nanoseconds long. And that person's in the middle of the pole. And we've said that x prime equals 0 at the left end of the pole. So if x prime is 0 here, then of course the person at the middle of the pole has to be at x prime equals 5 nanoseconds. In fact, any event that we might come up with involving the person at the center of the pole had better be at x prime equals 5 nanoseconds. And any event that we come up with involving the left end of the pole had better be at x prime equals 0. Even if after events A, B, and C, we added in events D, E, and F, corresponding to the runner passing by someone who hands them water, the left end of the pole passing by that person who handed them water, and so forth. Any event involving this runner had better be at x prime equals 5 nanoseconds. Any event involving this had better be at x prime equals x prime equals 0 nanoseconds. So that should make sense. Now let's talk about t prime b, all right? T prime b Well, that's when the person has reached the center of the barn. That happens 3 nanoseconds before this reaches the left end of the barn. Okay? Is that right? 0.6 times 0.4. Yeah, 3 nanoseconds. All right? Well, they have to be at the center of the barn before this reaches the left end of the barn, because they are they're ahead of this. And when they get to the center of the barn in their own reference frame, this is still sticking out. And because this is still sticking out in their reference frame, this has not yet reached there. Now, how long? Well, let's just go on a little bit. Okay, X prime A, position of left end of the pole when left door closes, T prime A, time when the left door closes, X prime B, T prime B. Let's now look at event C. X prime C is 10 nanoseconds. And it better be 10 nanoseconds, because any event happening here has to be 10 nanoseconds away from an event happening here. Whether the person's standing in the middle of the barn or somewhere else, whatever it is, any event happening here has to be 10 nanoseconds away from any event happening here. And this one, T prime C, if we plug in all the numbers, we get -6 nanoseconds. That better be even earlier than the person reaching the middle of the barn, because this reaches the right end of the barn long before this person's in the middle. And now let's talk about when that person's in the middle. In their reference frame, like we established, the barn is 6.4 nanoseconds wide. So 3.2 nanoseconds here, 3.2 nanoseconds here. Part of the pole that's sticking out is 1.8 nanoseconds long in the reference frame. It's 1.8 nanoseconds long, and they see the barn moving at a velocity of -0.6. So to cover that 1.8 nanoseconds, we're moving at a speed of 0.6. Well, time is distance over speed, so that's 1.8 over 0.6. That's 3 nanoseconds. It's going to take another 3 nanoseconds for this edge of the barn to move to there. And that is why this event happens at -3 nanoseconds. Any questions on that? All right. Then let's look at this event. This part of the pole sticking out is 1.8 nanoseconds also. And in the runner's reference frame, initially, this edge of the barn was right here. And then the edge of the barn moved until eventually the runner was located at the center of the barn, or the center of the barn had moved to the position of the runner. It would have taken, going at a speed of 0.6, the speed of light, it would have taken 3 nanoseconds to travel a distance of 1.8 light nanoseconds. And so, of course, that should happen 3 nanoseconds before the runner was at the center of the barn. And the runner was at the center of the barn at T prime B equals -3 nanoseconds. So the edge of the pole lined up with that 3 nanoseconds before that, or -0.6 nanoseconds. Thoughts, questions? Anyone? From another viewpoint, when the right end of the pole reaches the right end of the barn, there's 3.6 nanoseconds sticking out because the guy in the middle is 5 nanoseconds from the right edge. The barn is 6.4 nanoseconds wide, so 6.4 nanoseconds of the pole is inside the barn. 3.6 nanoseconds of the pole is sticking out. It's going to take that long. It's going to take 3.6 nanoseconds over 0.6 or 6 nanoseconds to cover this distance. Any questions at all? All right, well, if you don't have questions for me, then I have questions for you, and I think we're going to be able to vote on these. I think I was able to set it up. It says that I am logged in from another device, so my polling session is inactive, so let me try leaving the meeting on my other device. You can always log back in on that. No, I'm not logged in from another device. Let me do this. Hang on. Keeps telling me that I can't set this up for you to. I was so excited that I had learned how to, or thought I had learned how to use the polling feature. A couple weeks ago, did anybody see the Saturday Night Live episode? It was all about being stuck at home, and so there was a skit about people in Zoom meetings encountering all sorts of malfunctions and then doing all sorts of inappropriate things. Okay, you know what? That's not going to work. So let's just roll with this. All right. Let's start with this one. I want you to take a minute to work on it, and then we'll vote. Well, we won't vote, we'll discuss. All right, let's see here. It's going to be square root of 1 minus beta squared times its length in its rest frame. Beta is 0.5, so 0.5 squared is 0.25. So you got the square root of 1 minus 0.25, or the square root of 3/4. And remember that when a number is between 0 and 1, its square root is closer to 1. So the square root of 0.75 has got to be closer to 1 than, say, 3/4. So the only thing it could be was either 0.87 or other. Any questions? All right, now we've got an object moving at a speed of 4/5. In the other frame, its length is 15 nanoseconds. What's its length as observed in the home frame, which would be its own reference frame? Take a moment to think about that. Something's coming up in the chat. Well, let's see here. In the other frame, it's moving. The other frame is where you will see, in the other frame, it measures its rest length, right? So the other frame is the frame of that moving object. So its rest length is 15 nanoseconds. So it's got to be, oh wait, sorry, the object was at rest in the home frame. My bad, I didn't read the first one, I just went with the usual conventions. It's at rest in the home frame. In the other frame, it's moving, okay? The people in the other frame see it moving. Anybody who sees an object moving sees it as being shorter than it would be in its own rest frame. And so its rest length has got to be 15 nanoseconds over the square root of 1 minus beta squared, right? So 15 over the square root of 1 minus 0.8 squared. And it's helpful to just memorize that if beta is 4/5 or 0.8, square root of 1 minus beta squared is 3/5 or 0.6. It comes from that Pythagorean triple 3, 4, 5. So it's got to be 15 over 0.6. True or false? An object's length would be negative in a frame where it travels faster than the speed of light. I'm going to qualify this. So if beta is larger than 1, then yes, by following the math, the length would be square root of 1 minus something bigger than 1. So we're going to have an imaginary number here. But we should be a little bit careful with statements like that. Because it's impossible to go faster than the speed of light, sometimes people will say to me, but but what if you could? And the best answer to that is you're asking me what laws of physics we would have if we didn't have these laws of physics. And so I don't know that I can really answer the question, what would the length be if it were going faster than the speed of light? I can say what these laws of physics predict. I can say what sort of nonsense result these laws of physics predict, and therefore why we believe it's impossible. But sometimes people say, yeah, but technically, what if you could? Or hypothetically, what if you could? And the answer is you're asking me about the laws of some other universe, maybe a universe where string theory has been experimentally tested. All right, suppose an object is in a frame where it's moving at a speed beta naught, and its length is L naught, or it's a length that we measure, right? We see it moving. So we're measuring L naught, which is something other than the rest length. And then somebody doubles the speed. Is the object's length compressed by a factor of 2? Okay, this is the last time I use questions from the if its length is L1 when it's going at beta naught. Sorry about that. I should not be trusting publisher questions. This is why I write my own homework problems. All right, the formula for calculating length from rest length is not linear. And whoa, I forgot to edit that one as well. So let me try to, I was gonna be clever and do the subscript, but I'm not seeing it. Oh well. Yeah, it's not linear. So it's not like, it's not linear or inversely proportional. It's not either of those. So multiplying by 2 does not ultimately, the multiplying the input by 2 does not multiply or divide the output by 2. Any questions? Okay. In the pole and barn door problem, the barn never actually encloses the pole in the ground frame. True or false? I don't know what I thought. I see something. The barn never actually encloses it in the ground frame. It's the last time I used publisher questions. I just looked at what was in the book. I owe you guys an apology. In the ground frame, the pole has shrunk. So in the ground frame, the pole has shrunk to be the size of the barn. So I would say that that is false, that it does enclose the pole. And I promise this will not happen on Monday. Any questions on that? In the pole's frame, the barn certainly doesn't enclose the pole, but in the ground frame, it does. And it all comes down to the fact that for one object to enclose another, the two ends have to line up simultaneously. And simultaneity is something that people in different frames can disagree on. All right, subtle one. Could we also define a moving object's length this way? Yes, we could, because this would also give the exact same Lorentz contracted result as we derived at the beginning of class. All right. Final example, and then we'll probably wrap a little early. Space Wars paradox. We've got two craft of equal length, LR, and they have equal rest length, right? And so if we, when they line up with each other, in one reference frame, this one, if we're in the home frame, right, then we see this ship moving at 3/5. So we see this ship having been contracted by 4/5. And so we would say that this side of this ship, these two match up, And the front end of the other ship is more like here than here. To one ship. But to the other ship, this is what they would be standing, this is what they would be like. They would be the same length in their rest frames. But to this ship, it looks more like this. So they're going to disagree. If they were to fire at each other simultaneously, they're going to disagree on where those blasts hit, okay? If they were to both fire these two blasters simultaneously, right? If they were to fire their front and rear blasters simultaneously, we might say that they disagree on where the blasts hit, except that they can't disagree on where the blasts hit. And so the only conclusion to this paradox is that they are going to have to disagree on whether the blasters hit simultaneously. And I will let you work through that in the book. There's also an activity on this kind of paradox posted for today's recitation. And the homework will have a few more problems like this. On Monday, what we're going to do is we're going to talk about how velocities transform from one frame to the next. And then starting on Wednesday, we will talk about energy and momentum in relativity. Any questions before we go? All right, have a good day.